Okay, so we are supposed to set up but not evaluate an integral for each of these volumes. Find the volume of the solid generated when the region enclosed by y equals square root x, y equals 2, and x equals 0 is revolved about the y-axis. Okay, so I'm going to start by graphing these three curves, square root x, y equals square root x, y equals 2, and x equals 0. So square root x looks like 0, 0, 1, 1, 4, 2. That should be enough for square root x. Oops, it's an x. And then y equals 2 is this. And x equals 0 is the y-axis. So it's this region enclosed by these three curves. Shade that in. And I want to rotate this region about the y-axis. So this is a little bit different than the one in the demo. Going about the y-axis this time. So I want to choose a representative rectangle to rotate about the axis of revolution that is perpendicular to the axis of revolution. So somewhere between 0 and 2, I want to pick a random location along the y-axis. We'll call it y sub I. And I'm going to build a rectangle at that location. Some small amount of thickness, delta y. Right, because this distance is a y distance, so my thickness of this rectangle is delta y. And it's at a height of y sub I. So I need to know the radius, the length of that rectangle, because when I rotate that rectangle about the y-axis, I'm going to create a disk. And the radius of that disk is this distance, the height of the rectangle. So the height of that rectangle I can calculate. It's at a height of yi. I need to know this xi coordinate, right? What is that xi coordinate at a given height of yi? Well, I know the relationship between x and y along this curve, which is how I calculate the height of that rectangle. Y equals the square root of x. So I'm just going to jot that down over here. So I'm choosing y, and I need to calculate x. So to solve this for x, I get x equals y squared. So xi, this is y sub I squared. That's the radius of my disk. So capital R, the radius of my disk is y sub I squared. So maybe I'll draw a picture of the disk. This is y sub I squared, the radius. And then the thickness of my disk is delta y. So the volume of the disk is pi times the radius, which is y sub I squared, times the thickness of the disk, which is delta y. And then I'm going to add up all of these disks. So starting at 0, I'm going to have all of these little representative rectangles. Each one is going to get rotated about the y-axis, and I'm going to create these disks. I'm going to stack them up. So I'm going to have like n of these. I might start with 10 and then 100 and then 1,000. So I'm going to have a bunch of disks all getting stacked up along the y-axis. And so I need to add them all up. The volume of all the disks. Each disk has a formula pi times y sub I to the 4th, because squared is to the 4th, delta y, and I'm going to add up n of them. I have n of them, and then I'm going to take a limit as n goes to infinity. So my volume exact is the limit as n goes to infinity of the sum pi times y sub I to the 4th delta y. And that is the definition of an integral. It's a limit of a Riemann sum. So this is the integral, and to translate, I drop the subscript of I, and this becomes pi y to the 4th delta y becomes dy. And my bounds of integration are the starting and end points of my stacking of these disks. So I'm going to have the smallest disk down here starting at 0, and then I stack, stacking them up, and I keep stacking. Here was the representative one that I calculated the volume of. Keep stacking until I hit 2, y equals 2. So I'm going to stack from 0 to 2. Okay, now I want to find the volume of the solid generated when the region between the graphs of f of x equals 1/2 plus x squared, g of x equals x equals 0, and x equals 2 is revolved about the x-axis. So let's sketch each of these curves. F of x equals 1/2 plus x squared. So some points on that curve would be 0, 1/2, 1, 1.5, and 2, 4.5. So connect those. That's f of x. And then g of x equals x, so that would be 0, 0, 1, 1, 2, 2, like this. And between x equals 0, that's here, and x equals 2 here. So this blue region that I'm shading, that is the region that I'm supposed to rotate about the x-axis. So I'm going to draw a representative rectangle perpendicular to the axis of revolution. So I'm just going to pick a random location along the x-axis. We'll call this x sub I. And I'm going to draw a little rectangle at x sub I. And that rectangle is going to have some width, delta x. And when I rotate that rectangle about the x-axis, it's going to sweep out a washer. So if I draw the reflection of this rectangle over the axis of revolution, I'm going to have a sketch of my washer. Okay, so I need to know the inner radius and the outer radius of the washer. So the inner radius is the distance from the center to the closest point on the rectangle. So the center is at x equals, y equals 0, the y value of 0. And then this point is on the line y equals x. So this distance is x sub I. So little r is x sub I. And then big R, that's the distance from the center to the far point on the representative rectangle, this distance in green. So the center is y equals 0, and then this far point on the rectangle is on this curve, which is y equals 1/2 plus x squared. So big R is 1/2 plus xi squared. So the volume of my washer is pi times big R squared minus pi times little r squared times thickness. So I need a little bit more space to be able to write that all out. So I'm going to jump down here. So I have volume of my washer is, open a big parenthesis, pi times big R, which is 1/2 plus xi squared squared. Pi times big R squared minus pi times little r, which is just x sub I squared. And then the thickness is delta x. Now I'm going to add up n of these things, the volume of all the washers. This is the sum of n washers, where every washer has this volume formula. Pi times 1/2 plus xi squared squared minus pi times xi squared delta x. Then I take the limit as n goes to infinity. That gives me the exact volume of the region. The limit as n goes to infinity of all of this. And that is the definition of an integral. It's the limit of a Riemann sum, so this is an integral. And to translate from limit of a Riemann sum to integral notation, we drop the subscript of the i's, and we change the delta x to a dx. So this becomes pi times 1/2 plus x squared squared minus pi x squared dx. And then for the bounds of integration, I go back up to my picture and I look at where am I stacking these washers. I am stacking them starting at x equals 0, and I have all these representative rectangles that are going to get rotated about the x-axis and sweep out washers that I'm going to stack from 0 to 2. So I'm going to integrate from 0 to 2.